Okay, so good day everyone. Our topic for today is a continuation of the CPU scheduling, which is priority. So priority scheduling is a method of scheduling processes that is based on priority. In this algorithm, the scheduler select the task to work as per the priority. The processes with higher priority should be carried out first, whereas jobs with equal priorities are carried out on a round robin or first come first serve basis. Priority depends upon memory requirements, time requirements, and others. The types of priority scheduling is divided into two main types. The preemptive scheduling. The preemptive scheduling, the tasks are mostly assigned with their priorities. Sometimes, it is important to run a task with a higher priority before another lower priority task, even if the lower priority task is still running. The lower priority task holds of some time and resumes when the higher priority task finishes its execution. Non-preemptive scheduling. In this type of scheduling method, the CPU has been allocated to a specific process. The process that keeps the CPU busy will release the CPU either by switching context or terminating. It is the only method that can be used for various hardware platforms. That because it doesn't need special hardware, for example, a timer, like preemptive scheduling. So here is the characteristics of the priority scheduling. A CPU's algorithm that allows processes based on priority. It is used in operating system for performing batch processes. If two jobs having the same priority are ready, it works on a first come first serve basis in priority scheduling. A number is assigned to each process that indicates its priority level. Lower the number, higher is the priority. In this type of scheduling algorithm, if a new process arrives that is having a higher priority than the currently running process, then the currently running process is preemptive. So I will show you a video of an example on how we'll be able to get the milliseconds using a priority-based scheduling.
Alright, so let's get started. So in this priority scheduling, what happens is that a priority is associated with each process and the CPU is allocated to the process with the highest priority. So from the name itself, we can try to understand that in priority scheduling, what happens is that each process is having a particular priority. And based on their priority, the scheduling will take place. So the process that has the highest priority will be given the CPU first. And then the process which has the next priority will be given the CPU next, and so on. And if we have two or more processes with equal priority, then they will be scheduled in the FCFS order, which is the first come first serve scheduling order. So if there are two or more processes having the same priority, then the process that arrived first among them will be given the CPU first. So that is how priority scheduling takes place. So in the previous lecture, we have studied about the shortest job first scheduling, and here we can define the shortest job first scheduling in terms of priority scheduling like this. An SFJ algorithm is simply a priority algorithm where the priority is the inverse of the predicted next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. So the shortest job first scheduling is also basically just a priority scheduling where the priority is determined by the next CPU burst. So we have seen that in the shortest job first scheduling, the process with the smallest next CPU burst will be the first to get the CPU. So we can say that the next CPU burst or the predicted next CPU burst is the factor that determines the priority of this scheduling algorithm. So what we mean by this sentence, where priority is the inverse of the predicted next CPU burst. Why we say this is because the larger the CPU burst, when the CPU burst is large, then the priority is low. because a process having the shortest CPU burst will be the first one to get the CPU. So that process will be of higher priority. So the larger the CPU burst, the lower the priority. The smaller the CPU burst, the higher the priority. So that is what we mean by this sentence here, where the priority is the inverse of the predicted next CPU burst. So SFG algorithm also is simply a priority algorithm with this factor. So this priority scheduling can either be preemptive or non-preemptive. So we have talked a lot about preemptive and non-preemptive schedulings, and we know what it means. So priority scheduling can either be preemptive or non-preemptive. So let's see what it happens when it is preemptive and when it is non-preemptive. So what happens in a preemptive priority scheduling is that a preemptive priority scheduling algorithm will preempt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. So what happens is that if we are following a preemptive priority scheduling, then if the newly arrived process has a higher priority as compared to the process that is currently executing in the CPU, then the CPU will be taken away from that currently executing process and be given to the newly arrived process with higher priority. So that is what we mean by preemptive priority scheduling, and that is what happens in that. Now, what about non-preemptive priority scheduling? So in non-preemptive priority scheduling, what happens is a non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. So if we are following a non-preemptive priority scheduling, then if a new process arrives with higher priority than the one which is currently executing, even then the currently executing or running process will not be disturbed, but the newly arrived process will be just kept at the head of the ready queue. That means it will just be kept in the queue according to its priority. So if it is having the highest priority among all the processes in the queue, then it will be kept at the head of the queue. And then when the currently executing process completes its execution, then the newly arrived process will be given the CPU for its execution after that. So that is what happens in a non-preemptive priority scheduling. Alright, now let's take some examples to understand this in a better way. So here we have an example. Consider the following set of processes assumed to have arrived at time 0 in the order P1, P2, P3, P4, P5 with the length of the CPU burst given in milliseconds. So here we have a table with processes with process IDs P1 to P5, and here we are given their burst times, and here we are given the priority. So it says that they have arrived at time 0 in this order P1, P2, P3, P4, P5. And burst time is the time that a process will take for its execution. And here we are given the priority. So this is a priority scheduling. So with each process, there is a priority associated with it. So in some books, you will see that the higher the number or the value here, the higher will be the priority. And in some books, it may follow a different way where the lower the value, the higher the priority. So we will be following the second method where the lower the value, the higher the priority. That means here 1 will be the highest priority, 2 will be the next, 3 will be the next, and 4 after that, and 5 will be the least priority. So smaller the value here, the higher is the priority. So keep that in mind as we proceed with this example. Alright, so what we are going to do now is we will form the Gantt chart for this if these processes arrive in this order and if they have this burst times and if they are having this set of priorities. Alright, so let's see how we can form the Gantt chart for this. So using priority scheduling, we would schedule these processes according to the following Gantt chart. Alright, so let's see how we form this Gantt chart. So if we look at these processes, which is the process having the highest priority? So as I already told you, the smaller the value, the higher is a priority. So here process P2 has a priority of 1. So that means P2 is the one with the highest priority in this list that we have. So P2 will be the process to first get the CPU. So P2 gets the CPU over here. And how long will P2 execute? P2 will execute for 1 millisecond because that is the burst time of P2. So P2 executes from 0 to 1 milliseconds. Now, which is the next process that will get the CPU? So here we assume that they have all arrived at time 0. So they are all there present in the ready queue. So after P2 completes its execution, which is the process having the next highest priority? It is P5 with priority 2. So P5 will be the next one to get the CPU. So P5 will get the CPU after P2 completes its execution. And how long will P5 execute? It will execute for 5 milliseconds. So from 1 to 6 milliseconds. 1 plus 5 is 6. So up to the 6th millisecond, P5 takes the CPU and does its execution. Now after P5, what is the next process having the highest priority? It is P1. P1 has a priority of 3, which comes just after this priority 2. So P1 will be the next one to get the CPU after P5. And how long will it execute? It will execute for 10 milliseconds. So at the 6th millisecond, when P5 releases the CPU, P1 gets the CPU and executes for 10 milliseconds. So 6 plus 10 is 16. So up to the 16th millisecond, P1 executes. And after that, who will get the CPU? Let's see. P1's priority was 3. So what is the next highest priority after P1's priority of 3? It is P3 with a priority of 4. So P3 will now get the CPU and execute for 2 milliseconds. So 16 plus 2 is 18. So up to the 18th millisecond, P3 uses the CPU. And then after that, which is the next one to get the CPU, it is P4 with a priority of 5, and it is the last process. So P4 gets the CPU after P3 releases it at the 18th millisecond, and it executes for a burst time of 1 millisecond. So P4 executes from 18 to the 19th millisecond, and here it releases the CPU. So this is the Gantt chart for this priority scheduling when we have these processes that have arrived at time 0 and they have this set of priorities and this set of burst times. Alright, so now let's try to calculate the waiting time for this set of processes. So calculating the waiting times are very easy. You can just look at this Gantt chart and just write the waiting times here. Waiting time for P1, where is P1? P1 got the CPU at the 6th millisecond. So the waiting time for P1 was 6 milliseconds. So let's keep in mind that they have all arrived at time 0. So that is why we can just simply look at when they got the CPU in this Gantt chart and write the waiting times for this particular example. So what is the waiting time for P2 next? P2 was the first one to get the CPU, so the waiting time of P2 is 0 milliseconds. And for P3, what is the waiting time? P3 got the CPU at the 16th millisecond, so the waiting time of P3 is 16 milliseconds. And for P4, it is 18 milliseconds similarly. And for P5, what is the waiting time? We see that P5 got it at the 1st millisecond. So the waiting time for P5 is 1 millisecond. So what is the total and average waiting time for this? So the average waiting time will be 6 plus 0 plus 16 plus 18 plus 1 divided by the number of processes, which is 5, which gives us 41 divided by 5, which is 8.2 milliseconds. So the average waiting time for this set of processes when they follow a priority scheduling is 8.2 milliseconds. Alright, so now we have seen how this priority scheduling works. Now we have seen that so far it is very good, but is there any problem that we have with this priority scheduling? So can you guess about any problems that could occur if we follow this priority scheduling? So here is a problem that we have with this priority scheduling. So a major problem with priority scheduling is indefinite blocking or starvation. So what do we mean by indefinite blocking or starvation? Let's see. A process that is ready to run but waiting for the CPU can be considered blocked. So when a process is waiting and is ready to be run but has not yet got the CPU is considered as a blocked process. Now, a priority scheduling algorithm can leave some low priority processes waiting indefinitely. So this is the problem that we have. So there are processes waiting in the ready queue, ready to be executed and waiting for a CPU. But if there are some low priority processes that are waiting in the queue and there are many other processes with higher priority as compared to this low priority process, then what will happen? This process of low priority will get the CPU very late, or in a worst case, it may even never get the CPU, because let's say that there is a low priority process and then all the processes that arrive are having higher priority as compared to this low priority process. Then what will happen? All the higher priority processes will be getting the CPU, and this low priority process, since its priority is lesser as compared to those other high priority processes, it will never get the CPU. So in a heavily loaded computer system, a steady stream of high priority processes can prevent a low priority process from ever getting the CPU. So that is what I just explained. So in that case, the low priority process will be indefinitely blocked, or we also call it starvation. That means it is waiting to get the CPU, but it's never getting the CPU. It is starved from the CPU. So that is what we mean by indefinite blocking or starvation. So that is one problem which we have with this priority scheduling. So now what is the solution to this? Can you think of any solution that we can come up with in order to solve this problem of indefinite blocking or starvation? So here is a solution to that problem. A solution to the problem of indefinite blockage of low priority process is aging. So what do we mean by aging? Aging is something that we are going to use to solve this problem of indefinite blockage or starvation. So what is aging? Aging is a technique of gradually increasing the priority of processes that wait in the system for a long time. So what we mean by this is that when a process is waiting for the CPU in the system for a long time, then it ages. It will undergo aging. So when it undergo aging, what will happen is that we will increase the priority of the process as it ages. So if the process is waiting in the queue for a long time, so by the means of aging, we will increase the priority of that process gradually. So when a process is waiting in the ready queue for a long time, gradually by the means of aging, we will increase its priority. So when a process is waiting for a long time, slowly its priority also gets increased. And hence a time will come when its priority is also greater than some of the other high priority processes that have arrived, and hence that process will also get the CPU for its execution. So it will not remain there being indefinitely blocked or starving for the CPU. So the priority of that process gradually increases. So that is a good solution that we have to this problem of indefinite blockage or starvation. So let's take an example. If priorities range from 127, which is the lowest priority, to 0, which is the highest priority, we could increase the priority of a waiting process by 1 every 15 minutes. So if we are having this range of priorities where 0 is the highest priority and 127 is the lowest priority, then we can increase the priority of the waiting process by 1 every 15 minutes. So let's say that there is a process with a very low priority. Let's say the lowest priority of 127, and it is waiting, and there are many high priority processes coming and using the CPU, and this process is just waiting and waiting and waiting. So what do we do? After every 15 minutes, we are going to increase its priority. So in this case, increasing means this value have to decrease. 127 will become 126, and after the next 15 minutes, it will become 125, and after the next 15 minutes, it becomes 124, and so on. So after every 15 minutes, we are increasing the priority by 1. So what will happen? Eventually, even a process with an initial priority of 127 would have the highest priority in the system and would be executed. So even if all the processes arriving after that particular process is always of higher priority, even this low priority process, after a particular amount of time, its priority gets increased and increased and increased, and a time will come when that process will also be of highest priority, and hence it has to get the CPU for its execution. So we make sure that that process will get the CPU for its execution and it does not undergo indefinite blocking or starvation. So this is a good solution that we have to this problem. That is, by the process of aging, we are going to increase the priority of the processes as they wait in the ready queue. So that is the solution to the problem that we have in this priority scheduling. So I hope you're clear with that. That is how priority scheduling works, and that was the problem that we had, and this is how we solved the problem. So in the coming lectures, we'll be discussing some problems on this priority scheduling. So I hope this was clear to you. Thank you for watching and see you in the next one.
Okay, so this will be an example of priority scheduling with a problem and the solution. that is coming also from NESO Academy.
So here is a problem. Consider the set of processes with arrival time given in milliseconds, CPU burst time given in milliseconds, and priority where 0 is the highest priority shown below. None of the processes have I/O burst time. The average waiting time in milliseconds of all the processes using preemptive priority scheduling algorithm is blank. Alright, first of all, let's try to understand what this question is trying to ask. So here it says that we are given 5 processes with process IDs P1 to P5 and their arrival times given in milliseconds, which is shown here, and their burst times also given in milliseconds, which is shown here. And then we are having the priority of each of these processes shown in this last column. And then 0 is the highest priority. So if you see 0, this is the highest priority, and the next highest priority will be 1, then 2 and 3 and 4. So we are given this much of information. And then also it is said that none of the processes have I/O burst time. So what they mean by this is that here we are given the burst time. So burst time is the time that a process spends execution in the CPU. And I/O burst time is the time that the process spends for input-output operations. So here it says that it does not have any I/O burst time. So we just need to consider only the CPU burst times which are given here. Alright, so given these informations, we are to calculate the average waiting time in milliseconds of all the processes given above using preemptive priority scheduling algorithm. So we need to assume that the CPU is following a preemptive priority scheduling algorithm. And if it is following a preemptive priority scheduling algorithm, then what will be the average waiting time for this set of 5 processes? So that is what we are asked. And we are given 4 options: A29, B30, C31 and D32. So these options are very similar to each other. So if you are trying to guess, then you may have a hard luck. So let us see how we can solve this in the correct way and find out what is the answer. So coming to the solution, I have just copied down that same table here, and we are going to first form the Gantt chart for this. So the most important thing in solving this kind of problems related to scheduling is forming the Gantt chart. So if you are able to form the Gantt chart correctly, you can easily solve any problems related to this. So first of all, let's see how we can form the Gantt chart. And keep in mind that this is a priority preemptive scheduling. It is preemptive. So when a process of higher priority arrives, then if the priority of that process is higher than that of the currently executing process, then the currently executing process can be preempted, or the CPU can be taken away from it. So keep this in mind. Alright, so let's see how the Gantt chart for this can be formed. So here is a Gantt chart for this set of processes if they are following a preemptive priority scheduling. So if we look at this table, let's see which is the first process to arrive. So we see that P1 arrives at time 0. So P1 is the first process to arrive. And what is the priority of P1? It is 2. Since P1 is the first process to arrive and since there were no other processes at that time, so P1 will be the first one to get the CPU in this case. So P1 gets the CPU and begins its execution. And how long will P1 execute? It has to execute for 11 milliseconds. That is the burst time of P1. So did P1 execute for 11 milliseconds? No. Let's see why. That is because the next arrival time that we have is 2. At the second millisecond, P4 has arrived. So P4 arrives at 2 milliseconds, and let's see what is the priority of P4. The priority of P4 is 1. So is the priority of P4 higher than that of the currently executing process, which was P1? Let's see. P1's priority was 2 and P4's priority is 1. So always keep in mind that the lesser the value, the higher the priority. So here P4 is having the lesser value, which is 1. That means the priority of P4 is higher than that of P1. So what will happen? P1 will be preempted and P4 will get the CPU. So the CPU is taken away from P1 and P4 gets the CPU at 2 milliseconds. So how long did P1 execute? P1 executed just for 2 milliseconds and the burst time of P1 was 11 milliseconds. So if we subtract 2 from 11, P1 has a remaining of 9 milliseconds to execute. So P1 will still have to execute for 9 milliseconds the next time it will get the CPU. So right now P4 got the CPU and it's beginning its execution. So let's see, P4 continues its execution and let's see what happens. So what is the next arrival time that we have after P4? It is P2, which arrives at 5 milliseconds. So P2 arrives at 5 milliseconds and let's check the priority of P2. It is 0. So 0 is the highest priority that we have. So the priority of P2 is higher than that of P4, which was currently executing. So what will happen? P4 will also be preempted and P2 will get the CPU. So the CPU is taken away from P4 and P2 gets the CPU for its execution. So how long did P4 execute? P4 executed from 2 to 5 milliseconds. So that means it completed 3 milliseconds of its execution. And what is the total burst time of P4? It is actually 10 milliseconds. So from the 10 milliseconds, if we subtract this 3 milliseconds which was already executed, we have a remaining of 7 milliseconds for P4. So P4 will again have to execute for 7 milliseconds later when it gets the CPU. Alright, so let's see. So P2 now got the CPU and it's continuing its execution. Now if you look at this table, after P2, let's see what are the other processes that arrives. So after P2, which arrived at 5 milliseconds, the next process to arrive is P5, which arrived at 9 milliseconds. And after that, even P3 arrived at the 12th millisecond. So this 9 and this 12 all fall under this 5 to 33. That means during the execution time of P2, these two processes P5 and P3 arrived. But did they get the CPU? No. Why did they not get the CPU? Because the priority of P5 is actually 4, which is less than that of P2. And then the priority of P3 is also 3, which is also less than that of P2. So P2, as I told you, has 0 priority, which means the highest priority. So no processes will preempt P2 because it is of the highest priority. So P2 will actually execute for its total burst time of 28 milliseconds. So from the 5th millisecond when P2 got the CPU up to 33 milliseconds, 5 plus 28 is 33. So up to the 33 milliseconds, P2 uses the CPU for its execution. Alright, now at 33 milliseconds, P2 will release the CPU and let's see what are the next processes that we have and who is going to get the CPU next. Now if we look here, let's just cross out P2 because P2 has completed its execution. Now in the remaining processes, which is the process having the highest priority? So we have P1 with a burst time of 9, P3 with a burst time of 2, and P4 with a burst time of 7, and P5 with a burst time of 16. Now the arrival times doesn't matter because they have all arrived and they are all waiting in the ready queue. So among these 4 processes that are present in the ready queue, the process with the highest priority will be the next to get the CPU. So let's see. Here we have P1 with a priority of 2, then P3 with priority of 3, P4 with priority of 1, and P5 with priority of 4. So which is the highest priority? We have 2, 3, 1, 4. So 1 is the highest priority that we have among these 4. So P4 will be the one to get the CPU now. So P4 gets the CPU and it is continuing its execution. So how long will P4 execute? P4 has to execute for 7 milliseconds because it has already executed 3 milliseconds before and 7 was the remaining time it has. So it will execute for 7 milliseconds. So P4 continues its execution from 33 plus 7, which is up to the 40th millisecond. Now P4 also completes its execution. So let's just cross it out. Now in the remaining processes that we have, which is P1, P3 and P5, who is having the highest priority? P1 is 2, then P3 is 3 and P5 is 4. So among 2, 3 and 4, the highest priority is of P1, which is 2. So P1 will be the next one to get the CPU. So P1 gets the CPU at the 40th millisecond when P4 releases the CPU. And how long will P1 execute? P1 will execute for 9 milliseconds. So 40 plus 9 is 49. So up to the 49th millisecond, P1 executes, and after that, let's see what are the processes that we have now. So P1 also finishes. Then the only remaining 2 processes that we have are P3 and P5. So among P3 and P5, which is the highest priority? P3's priority is 3 and P5's priority is 4. So the higher priority is that of P3, which is 3. So P3 will now get the CPU and it will execute for how long? P3 will execute only for 2 milliseconds. That is the burst time of P3. So from 49 up to 51, P3 executes and completes its execution. Now the only remaining process is P5. So P5 will finally get the CPU when P3 releases it at the 51st millisecond. So P5 gets the CPU, and how long will it execute? It will execute for 16 milliseconds. So P5 executes from 51 plus 16, that is up to 67 milliseconds. So P5 execute up to the 65 millisecond, and at this point all the processes have completed their execution. So this is how we form the Gantt chart for a set of processes that follow a preemptive priority scheduling. So we saw that whenever a process of higher priority arrives, if the executing process is of lower priority than the one that has arrived, then the process having the higher priority is given the CPU, and the process that was executing currently was preempted. So that was a simple rule that we followed, and keeping that in mind, we have formed this Gantt chart. Now, if we have formed this Gantt chart, now the rest of the things becomes very easy. Now we have to calculate the average waiting time. So that is what our question was. So how do we calculate the waiting time for a set of processes that we have? So here is how we do it. Waiting time is equal to total waiting time minus number of milliseconds the process executed before minus the arrival time. So using this formula, let's calculate the waiting time for processes P1 to P5 and then see the average waiting time. So the waiting time for process P1 will be the total waiting time of P1. What is the total waiting time for P1? So to see the total waiting time, what you have to do is you have to look at the Gantt chart and see where did P1 occur the latest. So P1 occurred latest over here. This was the last occurrence of P1. So what is the waiting time for P1 during its last occurrence? It was 40. It got the CPU at the 40th millisecond. So that is the total waiting time of a particular process. So for P1 it is 40 minus the number of milliseconds the process executed before. So before executing here, did P1 execute any time before? And if yes, how long did it execute? So if you see in this Gantt chart, P1 executed even here. So, and how long did it execute? For 2 milliseconds. So minus 2 and minus the arrival time. For that you have to look at this table. So the arrival time of P1 was 0. So we have 40 minus 2 minus 0, which gives us 38 milliseconds. So that is the waiting time for P1. So similarly for P2, the waiting time is the total waiting time of P2. So where is P2? The last occurrence of P2 is here. P2 actually occurred only one time. So P2's total waiting time was 5 milliseconds minus the number of milliseconds it executed before. So we see that P2 did not execute before. So it is 0. And then the arrival time of P2. What is the arrival time of P2? It is 5. So 5 minus 0 minus 5, which is 0 milliseconds. So we see that in this table, P2 arrived at the 5th millisecond, and since it was of the highest priority among this set of processes, it was immediately given the CPU when it arrived, and it did not have to wait, and it was not preempted by any other processes because it is of the highest priority. So that is why the waiting time of P2 is 0. And what about P3? Let's see the total waiting time of P3. So the last occurrence of P3 is over here, and the total waiting time is 49 milliseconds. 49. And did P3 execute any time before? No. So the number of milliseconds the process executed earlier was 0. And then the arrival time of P3. For that we see this table and see it is 12. So 49 minus 0 minus 12 is 37 milliseconds. And similarly for P4, what is the total waiting time? P4 was here and also here. So the last occurrence of P4 is this one. So how long did it wait? 33 milliseconds minus the number of milliseconds the process executed before. So we see that P4 executed for some time even before this, that is here. And how much is it? It was for 3 milliseconds, 2 to 5, 3 milliseconds. So minus 3 minus the arrival time of P4. What is the arrival time? It is 2. So 33 minus 3 minus 2 is 28 milliseconds. And then the waiting time for P5 finally, how much is it? We see that P5 was the last one to get the CPU, and it got at the 51st millisecond, not anywhere before that. So the total waiting time is 51 milliseconds for P5. Number of milliseconds it executed before. We see that P5 never executed before, so it is 0. And then the arrival time of P5 was 9 milliseconds. So 51 minus 0 minus 9 is 42 milliseconds. So we have got the waiting times for this set of 5 processes. Now calculation of the average waiting time is very easy. So the average waiting time is 38 plus 0 plus 37 plus 28 plus 42 divided by the number of processes, which is 5. So that gives us 145 divided by 5, which is 29 milliseconds. So this is the answer to our question. So let's see if we have this 29 milliseconds in our options. So if we see our question, we see that option A is 29 milliseconds. So the answer to the question is option A, which is 29 milliseconds that we have just calculated. So that is how you calculate the average waiting time for a preemptive priority scheduling algorithm. And always keep in mind that whenever you are solving this kind of problems, the most important thing is to form the Gantt chart. So quickly form the Gantt chart correctly, and after that it becomes very easy to solve the problem. So I hope this was clear to you. Thank you for watching and see you in the next one.
Okay, so this time we have a problem number 1 with a solution. Consider the set of processes with arrival time in milliseconds, of course, CPU burst time in milliseconds at the same time, and priority shown here based on the given problem. So let's watch this from NESO Academy.
Consider the set of processes with arrival times given in milliseconds, CPU burst time given in milliseconds, and priority as shown below. And here higher numbers represent higher priority. If the CPU scheduling policy is priority non-preemptive, calculate the average waiting time and average turnaround time. So in the previous lecture that we have discussed, we solved a problem that was based on preemptive priority scheduling. But this question is based on non-preemptive priority scheduling. And here we have to calculate the average waiting time and the average turnaround time for this set of processes with process IDs P1 to P5, where their arrival times given here in milliseconds, burst times given in milliseconds, and priorities given here. And also note that in this problem, higher number represents higher priority. So in the previous problem that we solved, the lower the value, the higher was the priority. But in this case, the higher the value, the higher will be the priority. So if you look at this priority list, 5 is the highest priority and 2 is the lowest priority. So I'm taking this example because you should be familiar with the different kind of problems that can be there. So in some cases, the lower number may represent higher priority, and in some cases, the higher number may represent the higher priority. So pay close attention to what the question asks, otherwise you may make a mistake. So given this information, our task is to calculate the average waiting time and the average turnaround time. So let's see how we can do that. So in order to solve the problem, I have copied down the same table here again. And the first step, as we have already discussed many times, is to form the Gantt chart for this set of processes. Now remember that in the question it was said that this is a non-preemptive priority scheduling. So when we say non-preemptive, what it means is when one process gets the CPU for its execution, then until and unless it completes its execution, no other process will take the CPU away from it. That means it will never be preempted. So keep this in mind when we are forming the Gantt chart. Alright, so let's see how the Gantt chart for this can be formed. So here is a Gantt chart for this set of processes P1 to P5. So let's see what happens. Let's see which is the first process that arrives. If you look at the table, we see that P1 arrives at time 0. So P1 is the first process to arrive. Since there were no processes at that time and since P1 was the first one, it gets the CPU and it begins its execution. And how long will P1 execute? It will execute for 4 milliseconds because that is the burst time of P1. And then no processes will disturb P1 until and unless it completes its execution, because this is a non-preemptive priority scheduling. And also the priority of P1 is 2. So since there were no other processes at that time, we don't have to worry about the priority for this case. Now let's see. P1 is continuing its execution, and then at 1 millisecond, P2 arrives. And let's see what is the condition in our Gantt chart at that time. So at 1 millisecond, P1 is already executing. Now if you see here, and if you check the priority, you see that it's having a priority of 3. Now if you compare the priority of P1 and P2, we see that P2 has a higher priority. So keep in mind that in this case, the higher the numbers, the higher is the priority. So P2 has a priority of 3, which is higher than that of P1. But will it be preempted? It will not be preempted because this is a non-preemptive scheduling. So even though the priority of P2 is greater than that of P1, P1 will still not be disturbed. It will be allowed to continue its execution. So till the 4th millisecond, P1 continues its execution. So if you look at this table, we see that at 2 milliseconds, P3 also arrived, and at the 3rd millisecond, P4 also arrives, and at 4 milliseconds, P5 also arrives. So when P1 was continuing its execution from 0 to 4 milliseconds, at this portion of time, all the other processes have also arrived. And if you check the priorities, we see that P2 has priority of 3, P3 has a priority of 4, and P4 and P5 both has priorities of 5. And we see that all these priorities are greater than that of P1, which is 2. But even then, P1 will not be disturbed because this is a non-preemptive priority scheduling. So now we see that when P1 was executing from 0 to 4, all these other processes have already arrived and are now waiting at the ready queue. Alright, now at the 4th millisecond, P1 completes its execution. So P1 finishes his execution and the remaining processes are P2, P3, P4 and P5. Now they have all arrived and they are all waiting at the ready queue. So we don't have to worry about these arrival times anymore. So what we have to see is which among this set of 4 processes has the highest priority. So if we check here, we have 3, 4, 5, 5. So we see that P4 and P5, they are having the highest priority. So either P4 or P5 should be getting the CPU. Now if you look, we see that P4 and P5 has the same priority. So who should get the CPU? There is a tie over here. Now if we have this kind of a tie, in order to break the tie, we will be using the FCFS scheduling. That means the first come first serve scheduling. So if two processes are having the same priorities, then the process that arrived first among them will be the first to get the CPU. So if you see here, P4 arrived at 3 milliseconds and P5 arrived at 4 milliseconds. So P4 was the first one to arrive. So we will be giving the CPU to P4. So P4 gets the CPU and it will continue its execution for how many milliseconds? 5 milliseconds, because that is the burst time of P4. So from 4 to 9 milliseconds, 4 plus 5 is 9. So up to the 9th millisecond, P4 will continue its execution. So after P4 releases the CPU, who will get the CPU? It's obvious, it is P5, because P5 also had the same priority, but since P4 arrived earlier, the CPU was given to P4. So next, the CPU will be given to P5, and how long will P5 execute? It will execute for 2 milliseconds. So from 9 to 11, 9 plus 2, 11. Up to the 11th millisecond, P5 uses the CPU for its execution. Alright, so now we see that P1 completed, P4 completed, P5 also completed. So the remaining processes are P2 and P3. Now among P2 and P3, who has the highest priority? We see that P3 has a priority of 4, which is higher than that of the priority of P2, which is 3. So P3 will be the next one to get the CPU when P5 releases it. So P3 gets the CPU when P5 releases it. And how long will it execute? It will execute just for 1 millisecond, which is the burst time of P3. So from 11 to 12 milliseconds, P3 executes. And then the final process that we have is P2. So P2 will now get the CPU after P3 releases it at 12 milliseconds. And P2 will execute for 3 milliseconds, which is the burst time of P2. So 12 plus 3 is 15. So up to the 15th millisecond, P2 uses the CPU, and at this point, all the processes have completed their execution. So this is how we form the Gantt chart for a set of processes when they follow a non-preemptive priority scheduling. So here, since it is non-preemptive, it is a bit easier to form the Gantt chart because you are not going to preempt any processes, but keep in mind the arrival times. See the arrival times and see the priorities. So in this case, when P1 was executing from 0 to 4 milliseconds, all the other processes already arrived and were waiting in the ready queue. So we just had to see the priorities of those processes and assign the CPU to them one by one based on the highest priority. So now we have the Gantt chart. Now what we have to do is we have to calculate the average turnaround time and the average waiting times. So in order to calculate that, first we have to calculate the turnaround times and the waiting times for these set of processes one by one. So let's see if we can recall the formula for that. So here is a formula. So these formulas are same as the ones that we use for some of the other scheduling algorithms when they follow the non-preemptive form of scheduling. So the turnaround time is the completion time minus the arrival time. So we need to see when a process completed its execution, and from that, if we subtract the arrival time, then we get the turnaround time. And the waiting time is the turnaround time that we calculated here minus the burst time. That will give us the waiting time. So let us calculate the turnaround time and waiting time for all these processes one by one. Alright, so here we have a table in which we will be calculating the turnaround times and the waiting times. So first of all, we need to find out the completion times because that is required for calculating the turnaround time. So we have process with process IDs P1 to P5, the same thing. And let us see the completion times for this set of processes. So for P1, what is the completion time? So for getting the completion time, just look at the Gantt chart and see when the process released the CPU or completed its execution. So if you see P1, it completed its execution at 4 milliseconds. So that is the completion time of process P1. And for P2, what is the completion time? It is 15 milliseconds. And for P3, it is 12 milliseconds. For P4 it is 9 milliseconds, and for P5 it is 11 milliseconds. So this is very easy. Just look at the Gantt chart and fill this up. Alright, so let's calculate the turnaround time. So for process P1, what is the turnaround time? It is the completion time minus the arrival time. So what is the completion time of process P1? It is 4 milliseconds. What is the arrival time? It is 0 milliseconds. So what will be the turnaround time? It is 4 minus 0, which is 4 milliseconds. So similarly for P2, what is the completion time? It is 15. And what is the arrival time? It is 1 milliseconds. So what will be the turnaround time? It is 15 minus 1, which is 14 milliseconds. And for P3, what is the completion time? It is 12 milliseconds. And what is the arrival time? The arrival time of P3 is 2 milliseconds. So what will be the turnaround time? The turnaround time is 12 minus 2, which is 10 milliseconds. And similarly for P4, the completion time is 9. And then the arrival time is 3. So the turnaround time will be 9 minus 3, which is 6 milliseconds. And similarly for P5, the completion time is 11 milliseconds and the arrival time of P5 is 4 milliseconds. So that gives us a turnaround time of 11 minus 4, which is 7 milliseconds. So hence we have found the turnaround times for the set of processes P1 to P5. Now we can calculate the waiting times. So the waiting times can be calculated by turnaround time minus the burst time. So we have already calculated the turnaround times. So from that we have to subtract the burst times from this table. So that will give us a waiting time. So let's see, for process P1, the turnaround time is 4 milliseconds. And what is the burst time of P1? It is 4 milliseconds. So what is the waiting time of P1? It is 4 minus 4, which is 0 milliseconds. So we see that P1 was the first process to arrive, and even though it had a priority of 2, since it was the first process to arrive and since there were no processes at that time, P1 was given the CPU and it did not have to wait at all. And since this was a non-preemptive priority scheduling, P1 was not disturbed until its execution was complete. So P1 did not have to wait at all. So that is why the waiting time of P1 is 0 milliseconds. So similarly for P2, what will be the waiting time? It is the turnaround time 14 minus the burst time of P2, which is 3 milliseconds. So that gives us 14 minus 3, 11 milliseconds. And for P3, it will be turnaround time 10 minus the burst time, which is 1. That gives us 10 minus 1, that is 9 milliseconds. And for P4, the turnaround time is 6. And then the burst time of P4 is 5. So that will give us a waiting time of 6 minus 5, that is 1 millisecond. And finally for P5, the turnaround time is 7 and the burst time is 2. So we have a waiting time 7 minus 2, that is 5 milliseconds. So we have also calculated the waiting time for this set of processes P1 to P5. So now calculation of the average turnaround time and average waiting times are very easy. So how do we do it? The average turnaround time is 4 plus 14 plus 10 plus 6 plus 7 divided by the number of processes, which is 5, which gives us 41 divided by 5, which is 8.2 milliseconds. And similarly, the average waiting time is 0 plus 11 plus 9 plus 1 plus 5 divided by the number of processes, which is 5. That gives us 26 divided by 5, which is 5.2 milliseconds. So our question was to calculate the average turnaround time and the average waiting times for this set of processes when they follow a non-preemptive priority scheduling, and we have done that. So even here we see that the most important thing is to form the Gantt chart And after you form the Gantt chart, if you remember these formulas, we can easily calculate the turnaround times and waiting times and calculate the final answer.
Okay, so thank you very much now for our example video on how we'll be able to compute the milliseconds for the priority scheduling. So a while ago, I've mentioned about the characteristic of the priority scheduling. So a CPU algorithm that is schedule process based on priority, of course. So it used in operating system for performing batch processes. Then if two jobs having the same priority are ready, it works on a first come first serve basis. Take note of it. In priority scheduling, a number is assigned to each process that indicates its priority level. And we need to take note that lower the number, higher is the priority. In this type of scheduling algorithm, if a newer process arrives that is having a higher priority than the currently running process, then the currently running process is preempted. So what are the pros of priority scheduling? So easy to use a scheduling method. Processes are executed on the base of priority, so high priority does not need to wait for long, which save times. And this method provides a good mechanism where the relative importance of each process may be precisely defined and suitable for applications with fluctuating time and resource requirements. How about the cons or drawbacks? So if the system eventually crashes, all low priority processes get lost. If high priority processes take lots of CPU time, then the lower priority process may starve and will be postponed for an indefinite time. Then this scheduling algorithm may leave some low priority processes waiting indefinitely. And the process will be blocked when it is ready to run but has to wait for the CPU because some other process is running currently. If a new higher priority process keeps on coming in the ready key, then the process which is in the waiting state may need to wait for a long period of time or duration of time. A while ago, I mentioned this one. No? Lower the number, higher is the priority. So it depends upon to your professor. If your professor say that the higher number will be the priority, so you need to obey the instruction and always clarify with your professors. Okay. Then again, to summarize the discussion, priority scheduling is a method of scheduling process that is based on priority. In this algorithm, the scheduler selects the task to work as per the priority. In priority preemptive scheduling, the tasks are mostly assigned with their priorities. In priority non-preemptive scheduling method, the CPU has been allocated to a specific process. Processes are executed on the basis of priority, so high priority does not need to wait for long, which saves time. If high priority processes take lots of CPU time, then the lower priority processes may starve and will be postponed for an indefinite time. So that's it. And thank you for listening. Okay, so later on we have a quiz. Thank you and keep safe, everyone.